Welcome back. In previous class, we have seen the basic structure of the Cmos inverter, its characteristic curves, and we derived the equations for low level noise margin and high level noise margin. Now, let us see what are the different inverter configurations based on the pull-up device. The different configurations are passive resistor configuration, depletion mode NMOS transistor configuration, enhancement mode NMOS transistor configuration, and PMOS transistor configuration as a pull-up device. Okay, suppose if you use just a resistor as a pull-up device, that is referred as the passive resistor configuration. Suppose if the pull-up device is depletion NMOS transistor, that is depletion mode NMOS transistor configuration. In case of enhancement mode of NMOS transistor case, what is the pull-up device? Enhancement NMOS transistor. In case of PMOS transistor configuration, the pull-up device is PMOS transistor. So let us see each and every configuration. First of all, passive resistor as a pull-up device. So finally it is named as a NMOS inverter with resistive load. NMOS inverter with resistive load. You can see the diagram, the inverter diagram of the NMOS inverter with resistive load. The pull down device is what I said, always an NMOS transistor, enhancement NMOS transistor. But here the pull up component is a resistor, passive component resistor RL. Okay. Whereas the middle diagram represents the overlapped characteristics of transistor, pull up component and pull down component, pull up and pull down components. Whereas the third diagram represents the inverter characteristics with reference to resistor as a load. Okay. First of all, see the operation whether this one work as inverter or not. How can you see whether the diagram, whether the design diagram work as inverter or not? If you get the output as a complement of input, you can easily say this particular diagram work as an inverter. Okay. Suppose if the V input is 0, that is, what is the state of the pull down transistor or this NMOS transistor? It is in half state. Half state means acts as a open circuit, right? Acts as a open circuit. Hence the output is a open circuited voltage. You know, open circuited voltage is always maximum. That is here how much? Approximately equal to VDD. So VDD voltage we can see, right? So VDD voltage is considered as logic 1. Okay, so input is 0 volts means considered as logic 0. So the output is complement of the input. So in the first case, this circuit acts as an inverter. Coming to second case, let input is logic 1. That means apply VDD voltage at Vin. With such voltage, the transistor NMOS transistor acts as a on switch. On switch means it is considered as a short circuit. So the output is now a short circuited voltage. How much is the short circuited voltage? It is 0. Almost the short circuited voltage is 0. Okay, so very low voltage we are getting and it is considered as logic 0. So here also the output is complement of the input. So therefore this circuit work as a inverter. Okay, but here the problem is, so because of resistive load, high power consumption we can observe in this case, and you know the passive resistors are not suitable for the integrated circuit technology, and it occupies more space. Okay, and one more is when the pull down transistor is also in on, there is a static current flow directly from the VDD to the ground. So because of that high power consumption, you can see in the NMOS inverter with resistive load. Okay, now see the NMOS inverter using depletion mode transistor as a pull-up device. The slide representing first the diagram is the leftmost diagram is that inverter diagram using depletion mode transistor as a pull-up device, whereas second one represents the overlapped characteristics of both pull-up and pull-down devices, whereas third diagram represents the characteristic curve of this inverter. Okay, let us see first of all whether this circuit work as inverter or not. Coming to pull-up device, it is also a transistor of type depletion mode, and if you see here, the gate is short circuited with its source. That means what? The VGS is 0. So VGS 0 characteristics of this depletion transistor you need to consider. That is this characteristic curve, VGS 0 characteristic curve of the depletion transistor overlapped on the output characteristics of enhancement transistor. Enhancement transistor at various VGS voltages, right? So that means what? The depletion transistor almost in the VGS 0 characteristic curve. You know the VGS 0 characteristic curve of the depletion mode transistor. That means almost it is in on state. The pull-up transistor is in on state. Okay. Now, first of all, I am going to apply logic 0 value as an input for this inverter. That means applying 0 voltage at the input of the pull down transistor. With 0 volts at the gate of pull down transistor, its state is in the half state. Half state. It goes to the half state because very less gate voltage we are applying. That is 0 volts. 0 volts means less than the threshold voltage. That is the transistor in the half state. Half state means acts as a open circuit. So output is a open circuited voltage. That is the maximum voltage you can observe, almost equal to VDD, right? VDD voltage you can observe. So in the first case, that is input is applied as a logic 0, high output voltage we are getting. That high output voltage is considered as logic 1. So inverter operation is satisfied. Similarly, suppose if the input is logic 1, that means applying VDD voltage at the input of the this pull down transistor. With that voltage at the gate, the pull down transistor state is on state. On state is considered as a short circuit. Hence, the output voltage is a short circuited voltage. Short circuited voltage is 0. That is considered as logic 0 at the output. So in second case also we are getting a complement output with the input. So it satisfies the inverter operation. But what are the drawbacks here means when the output is logic low. When the output is logic low, what does it mean? The pull down transistor is in on. Already the pull-up transistor is in on. If both the transistor on means there is a direct current flow from VDD to ground. That is called the static current flow. Because of that current, the power dissipation is large, known as static power dissipation. You can observe in this transistor. I mean, the power dissipation is high in the depletion mode as a depletion mode transistor used as a pull-up device. Okay. Now see the points. The output is not ratioless, so which leads to asymmetry in the switching characteristics. That is the one of the drawback of this type of inverter. There is a static power dissipation when the output is logic low, because both the transistors are in on, so that the static current flow you can see, that's why the power dissipation is high. And its output is strong high output level but weak low output level. Okay, so because the pull-up device is depletion transistor, high output value we can get whatever the expected, but the low level value is not zero. But the low level value is not zero. Some voltage we can observe. Okay, that is treated as a low, weak low output level. Weak low output level. Now let us see what happens by using the enhancement transistor as a pull-up. Is it overcomes the drawbacks or not? So this is the inverter diagram using enhancement transistor as a pull-up, and the second diagram represents the inverter characteristics of it. Here, then to switch on the enhancement transistor, always we need to connect the VDD supply to both gate and drain terminals of the enhancement transistor. Then only the enhancement transistor is switched on always, because it is a pull-up transistor. Okay, then as usual the input is applied to pull-down transistor. Let us see whether this one acts as a inverter or not. If Vin is 0, as usual the pull-down transistor is in the half state, so acts as a open circuit. So output is a open circuited voltage, that is high voltage we are getting, but not equal to VDD, that voltage is VDD minus VTN. Okay, output voltage is less than the required value, that is VDD. Similarly, when the input is logic low, that is 0 volts, if you connected the gate of the pull down transistor, already with reference to pull 0 input we have seen. Now let us see the operation with applying logical 1 at the input of the pull down transistor. Logic 1 means VDD voltage we are connecting at the Vin. So with the VDD at the gate of the pull down transistor, it goes to on state. It goes to on state means acts as a short circuit, and output is a short circuited voltage, that is very less voltage we can observe, but it is not equal to 0. As usual in the previous case, the amount of voltage here is VTN, that is threshold voltage amount we can observe at the output. So here what will happen at both the logical low and logical high cases, the voltage degradation you can observe. Perfect voltages values we are not getting. That is one drawback here. And another drawback here also is, when the output is logical low, what happens, both the transistors are in on. Already upper pull-up transistor is in on. When output is low means the pull-down transistor also in on. So static current flow is there, hence static power dissipation you can observe. Okay, so these are the drawbacks. It produces weak low and high output levels. Both logic low and logic high outputs are at weak. And static power dissipation you can see. And it is also, the output is not ratioless, therefore asymmetry in the switching characteristics you can observe. Now to overcome these drawbacks, let us use Cmos transistor as a pull-up now. Cmos transistor as a pull-up. So when you use Cmos transistor as a pull-up, if you see the construction of an inverter, the resultant one is called Cmos inverter. It is called Cmos inverter. Why it Cmos? Cmos means complementary MOS. Why the name complementary? Because this technique uses both NMOS transistors and PMOS transistors. Here pull down transistor is enhancement NMOS transistor, pull up transistor is enhancement PMOS transistor. That's why it is called Cmos inverter. Okay, and the input is applied at the gate of both pull up and pull down transistors, and output is considered at the intersection of where the terminals jointed. See, in the diagram, the output is considered here where the pull up and pull down transistors are jointed. Okay, and the middle diagram represents the overlapping characteristics of pull down and pulled up transistors, and the third figure represents the inverter characteristics and flow of current in the inverter. Okay, first of all, see the operation, whether this one work as inverter or not, but that you can see in the next class.